Well, hi everyone. Thank you so much for joining the first machine learning and prediction modeling meeting. You know that we meet once every month, the last Wednesday of the month from 3 to 4 p.m. And we are very lucky to be listening to great speakers using, developing, applying machine learning and prediction modeling techniques. This is open, so any of you are already here, already joined, so you know that. But if your colleagues, your peers would like to join the meeting, they can do it freely, just following the links that we share in social media, in Twitter, and that I also shared throughout our email list. If you would like to take part on this or be joining our list, you just need to drop me an email here or drop a message here in the chat, and I will add your name to our mail list so that you can get all the information about these meetings. So again, thanks for joining, and particularly thank you to Mr. Lei Luo, who's our speaker today. Hi, Lei. We are very happy to have you with us. You were our former MSc student here at King's College London, and now you are joining us again to explain us a little bit of your research as data scientist, and you would like to present this novel convolutional neural network approach that you have been using for classifying brain states under image stimuli. So we're happy to be listening to you today. And yeah, we would like also to inform people that if you have any questions, you can post them in the chat. And by the end of the talk, we will be opening a time for questions and answers, a bit of discussion with our speaker. So thanks very much, and Lei, and please feel free to start when you are ready. Thank you.
Okay. Thank you very much for inviting me to join this seminar. I'm very honored to give the presentation of my master's project. Today, I'm going to introduce a novel convolutional neural network for classifying brain states. Okay, I'm going to start. First, let me introduce you some background of the neuroimaging and machine learning. First, machine learning in clinical utilization. The mechanism of human neural responses to different stimuli has always been of interest to neuroscientists. In current clinical situation, tools to distinguish different diseases or states based on the changes in neural functions are desperately required. And MEG is a neuroimaging technique which is very useful for detecting brain states and evaluating the behavior responses. It allows us to map and locate specific brain areas and ongoing functions. And in this project, I used the convolutional neural networks to develop a classifier for different brain states. As we know, with the increasing use of convolutional neural networks, the short name is CNN, in neuroimaging computer-assisted classification. An assembled classifier of CNN might be able to mine the hidden patterns from MEG signals. Some studies have shown that CNN offers a very unreplaceable advantage for patterns modeling. Those other techniques may not be able to reveal. However, develop an effective brain states classifier is a difficult task because of the non-Euclidean graphical nature of MEG signals. Just imagine if a picture, you want to distinguish if a picture is a cat or a dog, you can't use normal linear features to distinguish this map. You can only use some hidden patterns to distinguish this picture. So here, my classifier is doing this thing. I also extract the band power to inform the model. So in MEG signals, it reflects the brain activity, and the brain wave can be disposed in many different frequencies and can inform this model. In these years, the highly development of high performance computation is increasing. So we are using the deep learning instead of traditional machine learning to solve these problems. And this deep learning is doing much and much better performance. We Kings get access to a new cluster last year. It contains 40 A100 GPUs. So I'm using these GPUs doing the learning. Before introduce my model, I want to introduce a little bit information about convolution and max pooling. As we can see in the picture A, from the left stands for the raw data, and we use a 3x3 kernel filter to scan this 6x6 input data. And finally, this step gives us a 4x4 features map. So that's what convolution is doing. And in the below is a mass function of convolution. Here, F stands for input data and K stands for kernel filter, and it will finally gives us a features map in this form. And max pooling is data transformation. As we can see in B, max pooling comes to decrease the dimensions of data in order to keep more neurons activated, which is reported to reduce overfitting as well. And here's the data sets I'm using. MEG data from 24 participants collected with the CTF 275 channel axis gradiometer system. The recorded durations of each stimuli is 1.29 seconds, which is from 0.5 before and 0.79 after the image is shown. The MEG device is similar like what I wear in here. He actually is an EEG device. So a monitor is in front of the participant. Pictures are shown to the participants, and the MEG signals are recorded at the same time. So why is this thing is important, and why this model is useful? Here is a rationale. First, I would say the limitation of traditional clinical categorical methods. Classical classification methods have obvious shortcomings. It may not be able to be appropriate for behavior prediction or brain state classification, and they can be improved in classification accuracy by using those deeper learning methods. And there's only subtle differences, but in general, same patterns of the MEG signals. As we can see in this topographic map, for all of these different stimuli, 14 stimuli, those activated brain areas are quite similar with each other. So we cannot distinguish them with our raw eyes. And it's hard to distinguish them with traditional clinical methods. So here the similar it means we need an algorithm that is sensitive to these very small differences between stimuli. So CNNs are good candidate for solving this problem. So in the past decades, have seen the quick and the great revolution of artificial intelligence as the development of computer science. What is a big breakthrough takes us close to the scientific field are powerful tools that teach machines to learn techniques have gradually built their presence in recent decades. The applications in medical utilization lacks. So here I comes to try to solve this problem. My aim is to develop a CNN-based model with better performance in classification than traditional machine learning models, and test if the model can be improved with extra information adding relative power spectrum. Before we use a model, we do some pre-processing to the MEG signals. First, Maxwell filter. We use Maxwell filter to remove noise, and then a high-pass filter above 0.5 Hz and low-pass filter below 45 Hz is introduced. It allows us to get the signals of 95 variants. And then ICA, the independent component analysis, comes to separate the signal components. Those data was unsampled and the window width of data was set at 800 times later. So for those power bands, there are 6 types: delta from 0.5 to 4, theta from 4 to 8, low alpha from 8 to 10, and high alpha from 8 to 12, beta from 12 to 30, and gamma above 30 Hertz. It's actually below 50 Hertz because it's impossible to detect any information above 50 Hertz as we have unsampled the data at 100 Hertz. Here the R, here is a function of the relative power. The R represents the relative power of frequency band, and A stands for absolute power of the same frequency band. P's are the absolute power of all frequency bands. So we use Welch's method to extract the bands and derivative power spectral densities. The reason why I choose this function is because the function gives us single values for each trial, but other methods that only gives you a power at every time point, which is not I want. Eventually, the absolute and the relative power bands are transformed from the input data in the real number vector space is C multiply T to the C multiply F, which means we convert the space from 222, the number of channels, to 6, the number of frequency bands. And then I applied normalization. Normalization is used to normalize all input data because the normalization step can generalize statistical distribution of uniform samples. It is expected to enhance the training performance. Normalization is used here and helps to reduce data redundancy and improve the data integrity. At last, all of this data are normalized to from between 0 to 1. Next, I'm going to introduce my neural network architecture. It contains 4 blocks. First block is a spatial block. It is used to extract the spatial features from the raw data. Here, the first layer, each layer have their own functions. First layer, the first convolutional layer generates a feature map in a real factor from S plus S times 1 times T prime from input data in C multiply T. Here the C is channels number and S is the time is 46, where I set. It's a kernel length. And the second convolutional layer in the spatial block generates a feature map in S prime times 1 times T2 prime with the frequency features then. And afterwards, the data is downsampled with a max pooling layer and swapped along the axis between S and 1. It's converted from the S prime times 1 times T2 prime to the real space of 1 times S prime to T2 prime. So it's just a mass process. And this operation allows the data being considered as an image changing the convolutional direction. Then we feed this data, process the data to the temporal block. This one is designed to extract the temporal features from the data. The second block consists of 8 convolutional layers and 4 max pooling layers. Each max pooling layers are attached after every 2 convolutional layers. And the ReLU is the activation function for all of these convolution layers in this block. The kernel size of these convolutional layers is small and decrease every 2 layers in order to extract the local frequency temporal features from the output features map of the previous layer. Then I used an attention block. This attention block is composed of 2 parts, a channel attention block module and the spatial attention module. From this add and above is a channel attention, and the below is a spatial attention module. Those 2 modules help model focus more on the important information, the channel dimension and the spatial dimensions. First, for the channel attention module, input data process average pooling and max pooling separately. Where the average pooling layer is used to aggregate spatial information, and the max pooling layer is used to maintain more extensive and precise context information as images ages. The outputs are passed to a multi-layer perceptron network with a SAM weight, and this layer has a bottleneck, here, and the width and length of the number of these neurons are decided by a reduction ratio of 16. Then the sum of 2 outputs from this layer is given to the sigmoid activation function in order to project values in feature map into real space from 0 to 1. Finally, the channel attention modules return a feature map as a product of input and calculus scale, and then pass it to the second module, spatial attention module. Compared with the channel attention module, spatial attention seems to be a bit simpler, which includes 1 convolutional layer and the sigmoid activation function, the same as the channel attention module. The spatial attention module returns a feature map as a product of input from previous module and calculates scales in this module. And finally, it's a fully connected block. This fully connected block comes to play a role of classifier. It's projecting the distributed features of representation of the feature map to sample label the number of features space. So the following step is another fully connected layer. It's labeled as GMM. It's a general matrix multiply, which finally generates 14 features. It's a categories we want. And at last, data is passed to the softmax activation function to convert the numbers vector into the probability vector. So at last, we get the probability of each categories from the model. However, a very serious problem comes when I first developed this model. It's overfitting. Overfitting, I thought a lot of solution to solve the overfitting problem. First one is dropout to avoid overfitting. A 30% dropout is applied up the after the last 4 spatial convolution layer, and 50% dropout is applied up the first fully connected layer. Here. And then I used the SGD Optimizer instead of the Atom, which we know the Atom is a very traditional one, but SGD is reported to have a better generalization capacity compared to that Atom one. So, and it may, even though it may converge a bit slower. I set the initial learning rate as 0.005 and the momentum to 9. Momentum helps to accelerate gradient vectors in the right directions, and thus leading to faster conversion. And specifically for the second fully connected layer, a weight decay as 0.005 is set to avoid overfitting. The weight decay is a technique used in machine learning to reduce the complexity of model and prevent overfitting. I also use the dynamic learning rate. So for each learning steps, the learning rate are quite different. We can see in this function, if in the next learning rate is the performance is worse than the previous one, the learning rate will be multiplied by a lambda, and lambda is smaller than 1, so the learning rate will be decreased. Until the learning rate gets small enough, I start the early stopping in about 130 here in these trainings. Okay, here's an introduction of the model. Next is about the results. For the results, I don't know if you still remember, we extracted the relative power spectrum in the very beginning steps. We find that the beta and delta in concentration. So we inform the relative power spectrum to fully connected to the fully connected layer here is labeled as identity to the model, and it informed the model about the informations of frequencies, and it succeeded to to improve the performance of the model. And we compared the model with 2 baseline models. One is LSTM RNN. It is reported to be good to deal with those sequential data, because MEG data is a sequential data. And I used the simple convolutional neural net. It used a simple convolutional neural network to compare with this model. This simple convolutional neural network is used to classify the pictures of cats and a dog. Actually, in the second block, the spatial block, after we swapped the data, the processed data in spatial block here, in transpose steps, and fit it into the second block, it becomes a picture-like data. So this temporal block is doing a thing like picture recognition. So I used the simple convolutional neural network to compare with it. And finally, we find this model has a much better performance than those baseline model. It has 23.07% plus and minus 7.69%. Because random chance is 7.14%, which is 1/14. It's a random chance by random guessing. So we can say all of these models learn from MEG data signals, but this model is the best among these tested models. So the model has done is it converts the MEG signals from 810 epochs data of 800 times points in 272 channels to 14 categories. It allows us to get the chance of each brain states. I think there are generally two reasons for success. The first reason is because the model is successfully in imaging stimuli brain states classification, and the first part of the neural network extracted the correct features. Last layer classifiers the extracted features. And another reason is we used the relative power spectrum to inform the data in the finally fully connected layer. So I can say this model is feasible for analysis and classification of brain states. It may be considered as potential evidence that beta and delta waves are associated with brain states under imaging stimuli. And it may help researchers diagnose people in clinical situations and inform future neurological classifications approach in regard to high specificity and in identifying brain states. It's a very first research in doing these things. So I can say it's full of innovation, and it might inspire the following researchers about this brain states classification. So here's abbreviations of what appears in the slides, and some references are used in this presentation. Finally, I'd like to thank you, Dr. Toby Weiss. He's my master's supervisor who helped me a lot in this project. And I would like to thank you, the CREATE, because I used the computation resources is provided by the CREATE. Okay, thank you very much. Now is Q&A time.
Thanks very much, Lei, for the very interesting talk. It was at some point a little bit technical. I hope our audience could follow. We normally don't have talks so technical, but yes, that was really interesting. And no worries at all. And thank you, thanks a lot, Lei. That was very interesting. So yes, as Lei said, now it's time for questions. So if anyone has any questions, please just raise your hand, or you can also type it in the chat, and I will be very happy to read them for you. Yeah. So any questions for Lei?
Here we got one.
Yes.
How did you decide on the frequencies for the 6 channels that were used to represent the relative power spectrum? Did you compare your CNN to any other simpler models? Yes. Maybe I didn't make it clear enough. Here I compared this with Here I compared the model with STM-RN and the simple CN. I say because it's a very first research, the very first research about this brain states classification using deep learning models. So actually there are not quite a lot models we can compare with. I only got some machine learning models from other fields like picture recognition and the sequential data analysis. And how did you decide the frequencies? Yes, that's because in the previous research, we found each frequencies stands for quite different brain activities in your mind. Every time when you doing something different, your brain waves is going to be not the same. So, for example, the alpha, sorry, we always yes, for example, the alpha is associated with your movements, and like the theta is associated with sleeping. So it's decided by the literature review. Yes. For the other compared deep neural networks and RNNs is that a fair comparison. I mean, almost the same amount of parameters.
So this is the question that Lei is reading from the chat, which is from Ling Long Kian. Thanks very much, Ling Long, for your question. So I'm going to read it again too, so that everyone can hear well. So for the other compared deep networks like RNNs, is that the fair comparison? I mean, almost the same amount of parameters.
Yes. It's a good question because they are quite similar with it. The parameters of each other quite similar with each other, and actually the most parameters are in the fully connected layers. So for the LSTM, RNN, and simple CNN and my model, those parameters are quite similar with each other, and I think it's a fair enough comparison because LSTM and RNN and simple CNN actually they successfully do the classification of these brain states, but not to a very high accuracy.
Yeah, because my question is like if you use something in neural network, for example, if you like 10 layer CNN compared to 1 layer ASTM, and in that case, the big module with deep layers, the module has more large capability. So in that case, those large module may have a good performance than those smaller modules. So that's my question, mainly point 2.
Okay. Actually, this RNN and CNNs are composed with about 5 layers, 5 convolutional layers, and it's a little bit smaller than my model because my model is composed of about 10, 2 from the spatial one and 8 from the temporal. Then. Thank you for the question.
Yeah, okay, thank you.
Any of you would like to be
No.
added
That's not a question. That's not a question. It's me writing.
Okay,
yeah. Don't worry about this. If there's a question, I will read it. Don't worry. Okay. Is there any other question for Lei? So Shirin Elizabeth is saying, is it your approach is computationally greedy? Lei.
Yes, actually, I used one call from the A100. It takes about half an hour to test one participant. So if you want to test all of these participants, 24, it may take a lot of time.
I hope this is answering your question, Shirin. Thanks to you.
Yeah, thank you very much.
We would still have time for more questions if someone wants to ask anything else. So no questions in the chat and no hands being rising. Anyone else? Okay, so if there are no more questions, we would consider the discussion finished. Okay, so Leigh, thanks very much for the interesting discussion as well and for your talk today with us. And we wish you luck on everything you do and in your future applications with us, actually. Oh, there is something here. Okay, they are really so good. Thanking you for squeezing so much information into such a short space of time. That was really a great exchange. Thanks very much for joining, and that's totally true. You did a very good job,
I'm
Leigh.
a bit nervous today, so my speed maybe a little fast.
No. I think that was totally right. We could understand very well, and we could follow you very well. So
Okay,
thanks everyone for joining. We'll be here in the fourth Wednesday of February again with the machine learning and prediction modeling seminars. And thanks, Leigh, again for having been today with us. See you soon.
Thank you very much.
Thanks, everyone. Thank you.
For inviting me.
Read.